Please let them confirm, sir, if they can hear you. I can't hear you.
Now you should be able to hear me. That means all I've been saying, nobody has been hearing. Hello, class. Can you hear me now?
Yes, they can hear you now, sir. I can hear you now. So
Okay,
maybe you want to go back and I also
I have to go back. I've been speaking to her.
Yes, and I also just launched the YouTube channel now, so you can as well do that. Thank you, sir.
Once again, good afternoon, class. Apology for joining late. Now, today we'll be discussing elemental analysis of organic compound. You can remember that in the last class, we talked about the chemistry of carbon and the basis at which carbon form the plethora of compounds that it forms. We informed ourselves that carbon has the ability to catenate. Carbon, along with some other member of the group 4 elements on the periodic table, have the ability to catenate, and this ability we say is the linkages of those elements to form long chain, and that the ability to this ability decreases down the group. In order of carbon being the first member of that group has the highest ability to do this, and that is why carbon is able to form a whole number of compounds, and that gives you, give it its peculiarity in chemistry, that it has a branch of chemistry to itself. Now, we also said that this ability is prime on 3 ways, sp3, sp2, and sp hybridization, which leads to the formation of single bond, double bond, and triple bond, respectively. You can go back to revise what we said with regard to that. But today, we'll be looking at way by which you can determine the constituents of an organic compound. Remember that we form ourselves that an organic compound mostly contains carbon and nitrogen, but in some cases, it could also be compounded with some other elements like oxygen, nitrogen, halogen, sulfur, phosphorus, and even metals. One thing a chemist has to do is to determine the identity of a compound, and to know that, or to do the qualitative analysis of a compound. To do that, you have to come out with the constituent of the compound. That is, you want to know what the compound contains. With regard to carbon, you can do this by oxidizing the compound, subject the compound to an oxidizing an environment, which converts the carbon to carbon dioxide and the hydrogen to water. Invariably, you can now collect the carbon dioxide, estimate the amount, and that will give you an indication as to the amount of carbon contained in the compound. You can also do this for hydrogen by oxidizing the hydrogen to water, and you can now estimate the water. That gives you the amount of hydrogen that you have in the compound. So for the carbon and hydrogen, I said we subject it to an oxidizing environment. This is done by mixing the compound with copper-2 oxide and heating it up in a hard glass, a glass that will withstand the rigor of heat. When you do this, the carbon and hydrogen in the compound are oxidized. Okay, and if you look at the setup here, this is the sample that you want to determine its constituent, and you mix it with your copper 2 oxide and you heat it. As you are doing that, the carbon in the sample will be oxidized, react with the oxygen and converted to carbon dioxide. The carbon dioxide is now collected by passing it through your calcium hydroxide. This is collected and you can now subject it to further analysis. The water on its own is trapped by copper sulfate. And in the lab, the copper sulfate is more or less white, but in the presence of water, it turns blue to show that you've collected it. So the hydrogen present in the compound is oxidized to water, which condenses on the cooler part of the bulb. But what is the chemistry behind this little experiment that you are doing? The carbon, as you said, in the presence of the copper oxide is converted to carbon dioxide, which is now trapped and collected. This is passed into calcium hydroxide and it becomes calcium carbonate deposited. By estimating this, we'll be able to know the amount of carbon dioxide that you have. Then for the water, for the hydrogen, the same copper 2 oxide, it is converted to water. And when you now, in the presence of copper sulfate, it assumes the blue color, which shows that it has absorbed the water. So in so doing, you will be able to estimate the amount, via the amount of carbon dioxide that you generate, you'll be able to know the amount of carbon that is present in the compound, and the same thing with the water. For the other elements that may be present in the compound, you can qualitatively determine this by what is called the Lazarine sodium fusion test. Okay, the Lazarine sodium fusion test. These elements, when present in an organic compound, are converted into soluble inorganic compound by first fusing the sample or the organic compound that you are interested in with sodium metal. The nitrogen in the organic compound will be converted to cyanide ion, and the sulfur into sulfide ion, and the halogen into halide ion. Okay, so these are the reaction of what you are having. You take your sodium, molten sodium, fuse it with the sample. So all those elements that you have in the sample, apart from the carbon and nitrogen, which you have determined using the oxidation test, those other ions will now be converted into this. The sodium into its cyanide form, okay, the sulfur, the halide, and so on. So on having that, this fusion that you have, this compound or this compounded complex compound that you have that contains each of those elements that you are interested in is now taken and further test is performed on it. This is what I just explained now. So I'll just move to the next slide. So to now test for the presence of nitrogen, a few drops of iron 2 sulfate is added to about 2 ml of the Lazarine filtrate. The Lazarine filtrate you can have here because what you have fused together is now crushed. Okay, you crush it and grind it into a very fine powder and boil it for a few minutes and filter it. So you take a little bit of it. That is the filtrate that you obtain from it is what is called the Lazarine filtrate. A little bit of it is now used for the individual test. If you are looking for I hope you guys are still hearing me. I just need to do a quick check.
Yes,
sorry.
Sir.
Great. Oh, great. So you take a little bit of the filtrate, which will contain your sodium cyanide. You know, this sodium cyanide, the nitrogen in the compound is there now, and it is the nitrogen that you are looking for. You add it to iron hydroxide. The iron hydroxide you prepare freshly by the first reaction equation. So the iron hydroxide is now added to the lazine filtrate, which contains the sodium cyanide that contains the nitrogen you are looking for. And that gives you the cyanide form of the ion, which eventually will give you the sodium ferrocyanide. The sodium ferrocyanide will now give an indication of the amount of nitrogen that you have in the compound. This is all, the others are also treated in the same way. You take a little bit of the lazine filtrate. This is for sulfur, but in this case, you are reacting to it lead acetate, okay? And you get a black precipitate. That confirms that you have sulfur in the compound. For the nitrogen that we discussed before, your sodium ferrocyanide that you obtained from the previous series of reaction will give you, at the end of the day, a blue color. That confirms that you have nitrogen in the compound. Remember that this is qualitative test. You are not out to determine the amount of each of those individual elements, but you just want to know that if somebody, you happen to be in the chemistry lab and somebody comes with a sample and say, look, I suspect that this sample is an organic compound and it should have nitrogen, sulfur, or the rest. Please, can you help me test? So this test is just to give you an indication that yes, there's nitrogen there. To determine the amount of nitrogen is another business, which is beyond your level. But these are simple qualitative tests to determine the presence of each of those other elements. So for sulfur, again, you use your lazine. You can see it is just the lazine extract that we are using, but we are now using different reagents to test for the presence of those compounds. If you take your lazine filtrate and add your sodium nitroprusside to it, and you get a purple coloration, you will know that sulfur is part of the organic compound. So, for example, I can ask you a simple objective question that what compound is used to test for the presence of sulfur in your lazine filtrate? Know that it's sodium nitroprusside. Or what is the color that you obtain when you react sodium nitroprusside with lazine filtrate to test for the presence of sulfur? You know that it's purple coloration. Okay. Again, then if you want to test for the presence of halogen, we've looked at that of sulfur, we've looked at that of nitrogen. For the presence of halogen, then you take your filtrate again, the same, your same lazine filtrate, okay? You then add nitric acid to it. And again, you get your product, which one way or the other tells you that you have halogen present in the compound. So these are simple tests to determine the presence of these elements, apart from carbon and hydrogen, that will determine initially. So for those other series of halogen, you can see some of the reaction as stated. So you can go over them and read up on the rest of it. So quickly, on the slide, you also have tests for the presence of fluorine and some other ones. Detection of oxygen, that is, how do you know whether oxygen is present in your organic compound? This slide explains that. Then the test for detection of phosphorus and for other metals that may be present in the compound. So, I will know that. Then, how do we now go on a bit to determine the percentage composition and the amount of each of these compounds each of these elements in the compound? Like I said, we won't be going deep into quantitative determination of these elements in organic compound for your level, but we can do some sort of theoretical exercise on determining the amount of the compound. This brings us to empirical and molecular formula. I'm sure that this is not the first time that you would have come across such. Empirical formula on its own is the simplest formula you can give to an organic compound. For example, if you have an organic compound that is C2H, let's say H6, for example, C2H6, the empirical formula for that compound, you agree with me, will be what? CH3. So there's a way we can calculate this, and this is found under the topic of empirical and molecular formula. But let us just look at some simple examples that we can use to explain this. Let me see whether. Okay. Okay. Let's quickly discuss determination of percentage composition, for example. Let's say we have an organic compound, which is S gram. So let's say I give you that the mass of an organic compound is 12 grams. Or let's say 24 grams. Let me use 12. An organic compound X, you can write down the question. An organic compound X has a weight of 24 grams. So our X here will be 24 grams. Okay, and we want to determine the composition of carbon and hydrogen in that compound. But we've been told that when you eat the compound that has that 24 grams, if you eat it up, it's going to give you certain amount of carbon dioxide. So let's call that Z gram, as you have in this on the slide, Z gram. I'm going to give you certain amount of water. Let's call that Y gram. Again, remember that we have an organic compound as our sample that is weighing 24 grams. But out of that 24, if you subject it to oxidation, okay, it will give carbon dioxide of Z gram and water of Y gram. Now, you know that the carbon dioxide that you produce is an indication of the amount of carbon present in the compound. And the water that you produce is an indication of the amount of hydrogen present in the compound. So the question is, how do you now determine the amount of carbon that is present and the amount of hydrogen? So what you usually do is that you know that for every 1 gram of carbon dioxide, for every 1 gram of CO2, you are likely to have 12/44 grams of carbon. I hope everybody agrees with me on this. For every 1 gram of carbon dioxide that you have 12/44 grams of carbon. Where is that 12/44 coming from? 12 is the mass number for carbon. 44 is the mass number for the carbon dioxide. So simple ratio we give you is just like saying 1 gram of carbon dioxide contains 44 grams. Therefore, S gram of the carbon dioxide will contain what? So that will give you 12/44. Then, if you want to relate it to the mass of the compound that you have, it will now be 12/44 times 24. In this case, so if I do 12/44 times 24, that will give me the mass of carbon that is contained in that my sample. Okay, and if I say the sample only contains carbon and hydrogen, it means if I know the mass of carbon, I will be able to calculate the mass of hydrogen. I want you to do that for me now, everybody, on your own, and you post your answer as a chart. Then I'll be able to know whether you are following. So I'm saying that for carbon, if I have an organic compound that contains only hydrogen and carbon, and this organic compound weighs 24 grams, the question is, what is the mass of carbon in that compound? And I said, using the mass ratio, because we know that when you oxidize the compound, it's going to give you carbon dioxide. So if I use the mass ratio of carbon to carbon dioxide, which is 12/44, and I multiply it by 24, I should get the mass of carbon. When you get the mass of carbon, you just deduct that from that of 24. That will give you the mass of the hydrogen. And usually when you find this sort of question, I'm going to send an example of such question. You start with the carbon dioxide. When you use the carbon dioxide as the basis for the calculation, you get the mass of carbon. Then you can now deduct that from the mass of the sample that they give you to give the mass of hydrogen. And if the question goes further to say you should find the empirical formula, you can now divide both of the masses that you have by the atomic number, use the lower ratio to divide both, and you get a ratio that you can now ascribe to the carbon and hydrogen. Now, it must be noted that the procedure that we just discussed is just for a compound that has only carbon and nitrogen, and possibly oxygen in the compound. If sulfur, nitrogen, and hydrogen are present, there will be other appropriate steps to determine the amount of such in the compound. So let us look at some few explanations of some of the calculations. CHO is the empirical formula of acetic acid. Now, you agree with me that the formula for acetic acid is CH3 COOH, is it not? If you group all the elements together, just like looking for like terms. We have C2H4O2, is it not? So if you divide all through by 2, you will get CH2O. So CH2O is the empirical formula, but CH3COOH is the molecular formula for acetic acid. And that is different between molecular and empirical formula. Empirical formula is just a summary or an annotated form of the formula of the compound, whereby molecular formula gives you the detail of the constituent in that compound. It will give you the total amount of carbon, total amount of hydrogen, and any other element that is present in the compound. So it means that on the whole number ratio, carbon, hydrogen, and oxygen atom are present in the molecule of acetic acid in the ratio 1, 2 to 1, 1 to 2 to 1. The empirical formula does not tell us the exact number of various atoms that you have in the compound. Just like I explained, it's just like a summarized formula for the compound. But when you want to have a detailed formula, then you have to revert back to molecular formula. However, the exact number of atoms of different elements present in one molecule is always a simple multiple ratio of atoms, as expressed by the empirical formula. So, but again, you can also express this as the molecular formula, just like I explained. It means that the relationship between the molecular and empirical formula in the case of acetic acid is 2. N is equal to 2 here, because when you multiply the atoms in the empirical formula by 2, you get the molecular formula of the compound. So percentage composition of the compound can be calculated from its empirical formula. Okay, for example, if the empirical formula of acetic acid is CH2O, okay, the empirical formula mass will be 12, the mass number of carbon 12, plus mass number of hydrogen. Remember that hydrogen is 2. When you multiply it by 2, it gives you 2. And the mass number of oxygen is 16. If you add all this together, it gives you 30. Therefore, percentage of carbon in the acetic acid is 12 over 30 times 100, which is 40%. Percentage of hydrogen is 2 over 30 times 100, and that of oxygen will be 16 over 30 times 100. This is a straightforward calculation that tells you how to determine the percentage composition of substances. All you need to know is to know the empirical formula. Once you know the empirical formula, the mass number of each of the elements are not hidden. They are there for you to find out and see. So doing this simple calculation, you'll be able to calculate the percentage composition of each of those elements in the compound. So in summary, when you want to calculate the empirical formula, you take the following step. Step 1, the percentage of each element is divided by its atomic mass. This gives the relative number of different atoms that you have. In other words, to calculate the empirical formula, you must first determine the mass of each of the elements in the compound, which we try to do by using carbon dioxide and water, as I explained earlier. Once you get the mass for each of the elements, the next thing to do is to divide this mass by the atomic mass of each. If the mass of carbon, for example, is 24, you divide by 12. If the mass of hydrogen is 3, you divide by 1. If the mass of oxygen is 18, you divide by 16. That is what this step 1 is saying. The percentage of each element is divided by its atomic mass. The relative number of different atoms obtained are divided by the lowest that you have among them. If after doing step 1, you now have, for example, for carbon, you have 3 points, let's say 2. For hydrogen, you have 1.2. For oxygen, you have, say, 4.5. So you have 3.2, 1.2, 4.5. You now divide each of them by the lowest. By this example, it means 1.2 is the lowest. You divide everything by 1.2, 1.2. So whatever you now get will be the relative number of atoms present in the compound. The values obtained in step 2 may or may not be whole numbers. So sometimes you get fraction. I mean, you get decimal points for the division after you must have carried out step 2. But whatever you get, you round up to the nearest whole number. Okay, you round up to the nearest whole number. For example, if after I've divided, I'm getting 2.3, that means it is 2. Or after I divide, I get 2.8, that means it is 3. Round up to the nearest whole number. Minor fractions are neglected. So step 4, the symbol of each element present are written side by side in line with the number of atoms that you now have determined. So if after doing step 1 to step 3, I get carbon is 2, hydrogen is 3, oxygen is 1, it means my empirical formula is C2H3O1. So that is the simplest way by which you get empirical formula. After getting the empirical formula, the molecular formula can now be ascertained if the molar mass of the substance is known. Okay, usually if you're asked to do this sort of question, you'll be provided with the molar mass of the compound. If the molecular formula is N, the molecular formula will now be equal to N times the empirical formula, where N can be determined if the molar mass of the substance is known. One way by which you can determine N is equal to molar mass over empirical formula. So this is an example. Okay, what is the formula of a compound containing carbon, hydrogen, and oxygen, which give the following analytical result? I want you to do this in the next 3 minutes, and let's see the answer you will get based on what we just explained. Then going forward, I'm going to send a lot of test questions on molecular and empirical formula for you to read. So I'll be waiting for your answer in the next 3 minutes. So everybody should just do that and let's see the answer that you have. Okay. So I'm waiting for your answer. I can't see your answers, so I just need one or two people to be sure that you are following me. So somebody says C16H24O. I doubt whether that will be correct answer. C12H24O. Okay, C31H48O. Why am I C16H25O1? Okay, let's do it together. Let's just do it together. For carbon, we've been given the percentage composition, which is 82.34%. Then hydrogen is 10.62%, and oxygen is 7.04%. So carbon is 82.34. Hydrogen is 10.62, and oxygen is 7.04. So the first thing we do is to divide each of them by their atomic mass. We are dividing 82.34 by 12. We are dividing 10.62 by 1. And we are dividing 7.04 by 16. So if we do that, let me find my calculator. Just be checking whether it tallies with what you did. So if I divide 82.34 divided by 12, that will give me 6.86. At this stage, do not estimate. Don't avoid this temptation to estimate at this stage. So I'm going to write my own as 2.862. Okay? Then hydrogen 10.62 divided by 1 will still give me 10.62. Then oxygen 7. So oxygen is 7.04 divided by 16 will give me 0.44. So we have three values: 6.862, 10.62, 0.44. Of the three, 0.44 is the smallest. So we divide each of them by 0.44. 0.44, 0.44, 0.44. So that means for carbon, we have 6.862 divided by 0.44. That gives me 15.59. Then for hydrogen, I have 10.62 divided by 0.44. That will give me 24.14. And for oxygen is 0.44 divided by 0.44. That will give me 1. So if we now round up, it means our carbon will be 16, our hydrogen will be 24, and our oxygen will be 1. So that means our empirical formula will be C16H24O1. So how many of you got it? If you got it, if you attempted it and you got it, a round of applause for you. If not, okay, I can see. Yeah, I think a lot of people got it right. That is good. So I'm going to send more questions to you. So at this stage, this is the end of the first part of the organic chemistry series. Your next class, Dr. Ashikun, will take you through the rudimentary chemistry of the hydrocarbons. The hydrocarbons, I mean, alkane, alkene, and alkyne. Remember, we've done hybridization, so you have an idea of how those three groups of compounds forms. So, time for questions. You can post your question if you have any. If not, we call it a day. Next 2 minutes. You said? You have to come to science. You go and look for it. Come to science, you like to go to the lab. All right. Is there any question posted? Let's see. None. So that will be the end of the class. Thank you very much for joining.
Michaela is online, sir.
Okay, Michaela. Okay. Sir, please, what's the meaning of the difference between the 7.04? Which one is 7? Michaela, are you like asking it because I can't see your question? You can you? I can't see a question.
She raised her hand.
Okay, can you talk? Just talk. Probably it's an error. Some of them just. So I'm trying to track the 7.04 that is. Okay, the 7.04 here is. Okay, what this is saying is that if, for example, they give you the percentage composition of 2 out of 3 elements present in a compound, and you know that the total composition of all the elements will be equal to 100. So if you know 2, when you subtract the 2 from 100, it will give you the percentage composition of the third. That is what is meant by the difference, that is percentage oxygen will be the difference between the first 2 when you deduct it from 100. Okay? If you add this and this together and you remove it from 100, it's going to give you 7.0. That is what is meant. So in some question, you'll be provided with the 3 percentage composition. But in some question, you will be left with how to work out the percentage composition given the various mass of the element. Okay, in some of the questions I will send, you will see those different questions. Then you can have a practice on them and familiar with them. Then what is the color of respirate present in halogen? It depends on the halogen. If you look at the different reaction equation that I will send, you see that there are different colors for different metals that you have for the halogen. So just check and be familiar with them. So I think we have to call it a day. Thank you very much. Coordinator, sir, permission to fall out.
Permission granted, sir. Thank you very much. We appreciate your time, sir, in spite of your busy schedule. Thank you, sir.
Thank you, sir.
We expect your slides, sir. We expect to see your slides, sir.
You okay, sir. Today, I'll do it straight away, sir.
And the 30 questions, sir, for the test.
All right, sir. You are my boss. Sir. I will do that.
We appreciate you something, sir. Thank you, sir. Guys, see you on Saturday for the test.
What is the time of the test, sir?
It's going to be in the afternoon after their physics. I'm putting the questions together. I'm putting all questions together.
All right, sir.
Thank you, sir.